Today we're going to do a lesson on actually sketching the graph of a function. Here's our checklist. So I'm just going to kind of briefly go through this. We want to look for domain, intercepts, symmetry, asymptotes, all your first derivative stuff, which is increasing, decreasing, local maximums and local minimums. We want to look at concavity and points of inflection, which are the second derivative. And then we're going to take all this information and sketch the graph. As we sketch the graph, or as we find the information, I sketch the graph. So number 8 is kind of embedded as we're doing it. So don't leave the graph till the very end to sketch. Kind of sketch it as you're getting the information. By the time you're done step 6, you should have an estimate of what you think the graph is going to look like. And then usually I use checklist number 7 to check, do I have sort of the right graph happening. Now, below here, there is information about the summary of curve sketching, like kind of what each part relates to. But we're going to go through that with an example, and this file will be put on D2L for you guys. So today we're going to do an example of a rational function. And I'm going to do an example of an E function and a ln function. And then I'm going to give you a competency task that will help you sketch the graph of a function kind of on your own. So again, the first thing we want to consider is the domain. And I like to move in the order of that checklist because it kind of helps to know these things kind of as we're going. So the domain of a function for a rational, I need to think of what's a problem term. I know a problem term is when the denominator is equal to 0. This is a problem. So kind of my domain, I don't really need to justify it. I just need to find out where are my problem terms. My problem terms are going to happen where the denominator is 0. And I know that's going to be happening when x is equal to plus or minus 2. So x is not allowed to equal plus or minus 2. But other than that, x is allowed to be any real number. So that was step A or step 1. B, I'm going to do my intercepts. It's important to know where the graph is crossing on the x and y axis. That's kind of a huge characteristic of graphs. So my x-intercepts, just like before, we set y equal to 0, solve for x. So 0 is equal to 2 x squared minus 9 over x squared minus 4. So in order to do the x-intercepts, I set the denominator or set the function equal to 0. That means the denominator goes away when I multiply both sides by it. So it's literally when the numerator equals 0, kind of the simplified numerator. So my numerator is going to equal 0 when x squared minus 9 is equal to 0. And we know either by factoring or moving over the 9 and square rooting both sides, that would mean x is equal to plus or minus 3. So when I summarize my intercepts, I'm going to write them as ordered pairs. And when I give you the competency task, I would like you to prepare your solutions kind of in a similar format. I'd like you to highlight your final answers for each section so it makes the readability easier. My y-intercept, I'm going to set x equal to 0 and solve for y. So y is equal to 2 times 0 squared minus 9 over 0 squared minus 4. I clean that up. I get negative 18 over negative 4, which is 9 over 2. Now, in this sort of example, it's important to see that decimals are a little bit better. However, when you're presenting your example, sometimes exact values are better. So what we're going to do is we're going to write our y-intercept as an ordered pair and summarize that. Now I'm writing it as a decimal, but this decimal stops, so it's okay. So there's my intercepts. So now, as I go along, I'm going to set up a sketch of my graph as I go along. I don't want to wait till the very end to sketch this information. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Let's look at our information. 3, 0, minus 3, 0. So I'm going to use a different color. Minus 3 and 0. 3 and 0, we know these are points that the graph goes through. And then 1, 2, 3, 4, 5. At 4.5, the graph has a y-intercept. And my domain is x is not allowed to equal plus or minus 2. From 30-1, we know that that's going to be a vertical asymptote. So, I mean, I know here these are vertical asymptotes, but again, when we get to that step, we'll calculate them. But we already know that those are vertical asymptotes from 30-1. So I'm just going to come in and put these dotted lines in. These are important to know because these break up the graph into sections, and those sections will affect how the behavior of the graph is between these sections. So this is x equals minus 2, and so far that's the information I know based on what I've found. Okay, let's keep moving along. Step C is to do the symmetry. Now, we briefly talked about this in class. We want to figure out if the function is even, odd, or neither. So what we do is we compute f of negative x. If it's equal to negative f of x, kind of a negative on the outside, and then the function looks identical, we call this an odd function. And if I compute f of negative x and it's equal to exactly my function, it's considered even. If it's neither of those, we just say neither, so no symmetry. So let's compute f of minus x. This is 2, bracket. We sub in a negative x everywhere we see an x. So this gives us 2, x squared minus 9 over x squared minus 4. Now you're going to notice that this looks identical to the original function. So I'm going to call this equal to f of x. And based on my information, we know that f of x is even. So I'm going to come and highlight that because I'd like you to summarize each section. So that means when I draw this graph, this left side of the graph is going to be identical to this right side of the graph, kind of as a mirror image. Okay. Okay, symmetry. D. Asymptotes. Now, we want to do the asymptotes like we did in our outcome LC3. If we have a vertical asymptote, we want to do the limits to support that vertical asymptote. If we do a horizontal asymptote, we're going to take the limit as we go to infinity and minus infinity to justify that as well. So we already know that the vertical asymptotes are x equals plus 2 and x equals minus 2. But I do want to compute these limits to kind of show me further behavior. X approaches 2 from the right, and I want to do limit at, or I'll move that down here, limit as x approaches 2 from the left. So let's compute this. Limit x approaching 2 from the right of 2x squared minus 9 over x squared minus 4. I sub in 2. 2 times 2 is 4 minus 9 is negative 5. So this is 2 times negative 5 over 0. Now we want to figure out, is this 0 kind of slightly a positive number or slightly a negative number? So when I come in from 2 from the right, I'm choosing a number like 2.01. I sub it in. When I square it, it's going to be slightly bigger than 4. So this is a negative number over a 0, slightly positive. So that gives me negative infinity. And then when I compute the other one, limit as x approaches 2 from the left of this expression. This would give me 2 times negative 5 over 0. That part stays identical, but now when I choose a number coming in from the left of 2, like 1.99, it's slightly smaller than 2. So when I square it, it's going to be slightly smaller than 4. So that's going to be slightly negative. And therefore, 2 negatives will make this go to positive infinity. Now I'm going to move this expression over here a little bit. When x is equal to negative 2, I want to do my limit as x approaches negative 2 of my function. So this time I'm just going to sub the function right in. So if I'm coming in from negative 2 from the right, my number is negative 1.99. I square it, it's going to be slightly smaller. So this is 0, slightly smaller. I'm going to do 2 times 4 minus 9 again, which is negative 5. This time I go to plus infinity. So that's negative 2 from the right. When I compute limit as x approaches negative 2 from the left, I'm subbing in a value like negative 2.01 when I look at kind of my number line here. And so that's going to give me 2 times negative 5 over 0, but that's going to be slightly positive because when I square a negative, I get a positive and it's slightly bigger than 2. So my answer is going to be slightly bigger than 4, and therefore this will go to negative infinity. How does this help us on our graph? So as x approaches 2 from the right, this is going up to plus infinity. As x approaches 2 from the left, whoops, I made a mistake here. As x is approaching 2 from the right, we're going down to negative infinity. So down here, as I approach 2 from the right, or the left, we're going up to positive infinity. So I know something like that is going to happen. As x approaches negative 2 from the right, I'm also going to plus infinity. You can see how this even symmetry is coming in because this is kind of a reflection about the y-axis. And as x approaches negative 2 from the left, I'm going down to negative infinity. So it is sort of supporting the even symmetry that I got, so I know that I'm sort of on the right track. Okay, now we need to do horizontal asymptotes. I'm going to kind of just move my graph over. Move it some more down. Okay, so let's continue. So with horizontal asymptotes, we need to kind of do the limits before we know the values of the horizontal asymptotes. So limit as x approaches infinity of my function. Now you're going to notice I'm going to factor or distribute the 2 in, just because it makes it a little bit easier to deal with. The technique when I do this is divide by the highest power on the bottom, which is x squared. So when I do that, I get 2 minus 18 over x squared divided by 1 minus 4 over x squared. You still want to use your calculus to get this answer. This is 2 divided by 2 minus 0 over 1 minus 0, which will be 2, which means that y equals 2 is a horizontal asymptote. Now, when you look at this step, it makes no difference whether my infinity is going to plus infinity or minus infinity. So I'm going to kind of show this as both the calculations in one because I'm still going to divide by the highest power anyways. Now, how am I going to represent this on my graph? As x goes to infinity, my y value is going to approach 2, but you're going to notice I'm only going to show the 2 kind of on the ends of the function because if I make the dotted line go all the way through, I don't want it to confuse you because the graph is allowed to cross at y equals 2 in between, but at the ends it won't. So there's my horizontal asymptote on both sides. Again, I'm going to come back and summarize my information, the key parts of it, and then the work that supports it can be underneath without being highlighted. So there's my vertical asymptotes, there's my horizontal asymptote. Now we are going to go through all of our first derivative stuff. So I'm going to kind of classify all of that as first derivative Okay, so let's go through. First thing we need to do is find the derivative. So I'm going to take my original function. Now when I do my original function, you're going to notice I'm going to distribute the 2 in. And the reason for that is I want to kind of avoid extra product rules or anything like that. I just want to keep the derivative simple. So to do my derivative, it's going to be quotient rule. The derivative of the top times the bottom. X squared minus 4. The quotient rule says we subtract. We're going to leave do the derivative of the bottom, which is 2x, times the top over the bottom squared. Now, for all this time we've been doing derivatives, the simplification doesn't matter, but here we want to go through and actually get through the bulk of the simplification. We're going to distribute the numerator because there's a subtraction sign here, and I want to try to get rid of all the extra subtractions. I kind of want to leave it in a condensed factored form. So I'm going to distribute the numerator out. So I get 4x cubed minus 16x minus 4x cubed plus 36x all over my bottom squared. Now you don't want to distribute the bottom out because it is already condensed. I'm going to clean up my like terms. 4x cubes cancel out. I simplify that up. So 36x minus 16x is 20x over my denominator squared. And that is my simplified first derivative, and I'm going to kind of highlight that. That is key information. That's helping me deal with my first derivative information. So again, I'm going to come back and move this graph down. Some of my graph got cut off. We'll kind of include that in later. Okay, so now when I have my first derivative information, I want to represent that on a number line. So I need to find the critical numbers. Where is my derivative going to equal 0? That's coming from the numerator. So I'm just going to take my numerator, 20x, set it equal to 0, and solve for x. So x equals 0 should be on my number line. I want to do f prime of x being it does not exist. So this is telling me where is my function not differentiable. It's not differentiable when the denominator is 0. So x squared minus 4 has to equal 0, which would give me x equals plus or minus 2. Now I want to note that there's vertical asymptotes here because these points are not in the domain of my function. So when I do my number line, these are points that cannot be classified as local maxes, local mins, because they're not in the domain of my function. So I'm going to draw my number line. So 0 goes on here, 2 goes on here, -2. I'm going to specify that these were vertical asymptotes so I don't accidentally classify them. We're going to test the sign on the first derivative. So I'm going to choose a value in this section. So say I choose x equals 3. I'm going to sub it into my derivative expression. So that's going to be a positive on the numerator because 20 times 3 is positive. You'll notice my denominator is always positive because I'm squaring something. So that's positive. Positive, say x is equal to 1. So that's going to be a positive. Again, divide by a positive. I get a positive result. I'm going to take x is equal to -1. I sub it in. I'm going to get 20 times -1, which is negative, and my bottom is still positive. And then if I take x is equal to 3, I'm going to get, -3. 20 times -3 is negative, and the denominator is always positive. So therefore, this result is negative. I want to say, what does that information tell me about my first or my original function? A positive derivative means my function is increasing, and a negative derivative, this one should have been negative, my apologies. A negative derivative means the function is decreasing. So now I need to summarize my intervals of increase and decrease. F of x is increasing on 0 to 2 union 2 to infinity. We want to cut it off at these critical numbers because f prime of x is greater than 0. F of x is decreasing on negative infinity to negative 2 union negative 2 to 0 because f prime of x is negative. So these are going to be highlighted. Those are part of my main answer. The question is not only about sketching the graph, but also finding the information. Now you'll notice that the function goes from decreasing, so kind of going down, to going up. So that means or I'll just write it like this, a local minimum at 0, I'm going to box this number in because I have to find it because the derivative changes from negative to positive on a point that's in the domain of my function. I'm going to also summarize that there's no local max because I don't have any sign switches from positive to negative. So I'm going to highlight all this. We do need to find this y-coordinate. To find this y-coordinate, we sub it back into my original function. And you'll notice we've already done this calculation. This was my y-intercept. So minus 18 over negative 4, which was 9 over 2, which was 4.5. We already had found that. So now let's try to draw this information on my graph just to see, do I have a rough sketch of what's happening? Okay, so this graph has a local min, and we know that those arrows are going up. So that means that the graph kind of has to go up to this asymptote, up towards that asymptote, and it has a local min at that point. Now we also know that this part had to go down to infinity, and because this is a horizontal asymptote, I can also draw my graph sort of approaching that horizontal asymptote. Get rid of this down arrow. And I also know that the graph is symmetrical about the y-axis, so this should also reflect in the y-axis. And so I have a rough sketch of my graph here. Now if I check, the function is increasing on 0 to 2 and 2 to infinity. So you can see that the slope is positive here and here for all of that section. You can kind of, it's still increasing, but just a smaller value. And my slope is decreasing when on the other two sections. So that information coincides with the information I've already found. So this looks like my graph, but I still need to do my second derivative information to kind of confirm whether this graph has the proper smiles and frowns in the proper spots. So I'm going to just kind of cut this out again, move it down. We're going to do our second derivative, and I mean, by the end of this first derivative information, you should have a rough idea of what your graph is going to look like, and we're going to use the second derivative to just kind of confirm what we already may or may not know. So this is, what letter are we on? We are on F. And I'm going to just call it second derivative stuff. And so again, the graph and the information finding it is part of the question. So if your graph is right, but your information is wrong, you're still not going to get full credit on a question like this. Now you're going to notice I'm going to do my second derivative. Now my second derivative here is also going to be quotient rule, but it's also going to involve chain rule because of my denominator. So let's go ahead and do the second derivative. The derivative of the top times the bottom minus, I leave the top the same. Now I'm doing the derivative of the bottom. So I'm going to bring down the 2 bring down the 2, leave my inside the same to the power of 1, and then I do the derivative of the inside as part of chain rule, divided by the bottom squared, which will now put this at a power 4. Now before you go crazy and do distribution on the numerator, you want to notice that the bottom term, this piece, and this piece all have at least one x squared minus 4. So what I'm going to do first is divide the top and bottom by x squared minus 4. I'm going to be left with one of these x squared minus 4s on the top. I'm going to leave all this identical. And that x squared minus 4 will cancel out. So one of those cancels, and when I take one of them out of here, I get cubed. So every quotient rule that's kind of a rational function like this will always simplify like this first. So now what I'm going to do is I'm going to multiply all of that stuff together, and I'm going to distribute the 20 with the first two terms here, because I have to open it up because of that minus sign. So we get 20x squared minus 80 minus 20 times 2 times 2 is also 80x squared. My denominator cubed. And one more cleanup step to deal with the like terms, the 20 and the negative 80. It's negative 60x squared plus or minus 80 over my bottom. Now you'll notice that there's a common 20 in both of the numerators. I'm going to factor out a negative 20, and I'm going to be left with 3x squared plus 4 over bottom cubed. So this here represents my simplified derivative. Again, I want to highlight it because that is kind of key information as part of my solution. Now we're going to do the same information we did before. We're going to say, where does the second derivative equal 0? It's going to be coming from the numerator, but there's no possibility, because if I take 3x squared plus 4, I set it equal to 0, I subtract 4 on both sides, I'm not going to be able to take the square root of a negative, so there's no solution coming from the top. Where is the second derivative undefined or does not exist? It's going to be when x is equal to plus or minus 2. And I'm also going to just state here that these are vertical asymptotes, so I don't accidentally classify them as any inflection point. So I'm just going to kind of quickly show this here. So 3x squared equals negative 4. X squared equals negative 4 over 3. And again, you can't take the square root of a negative, so we have no solution. So I'm just going to say no solution here. So this time on my number line, the only things that section off my graph are my vertical asymptotes. And we know that those section off the graph. The graph can pass through these vertical lines. So we're going to test our values in this second derivative and say something about the original function. So I'm going to take x equals 3. So this expression is always positive. So my numerator is always negative because I'm timesing it by a negative 20. And my denominator is going to alternate signs. So if I sub in a 3, 3 squared is 9. My denominator is going to be positive. So that step is positive. If I sub in 0, my numerator is always negative. And my bottom, 0 squared minus 4 cubed, will also give me a negative, which means that this one is positive. And I can see I did the same thing. That should be negative. And then if I test a number like negative 4, my numerators are always negative. I take negative 4, I square it, I get a positive number bigger than 4, and I cube it, I get a positive. Negative overall, but positive for the denominator. Take your time doing that step. I don't need to see this. You can do that all in your head and just show me these signs summarized. With the negative means that the function is doing a frown or going concave down, concave up, concave down. So we just need to summarize that information. And I'm going to pull this graph down again. So f of x is concave up on -2 to 2, and my because statement, the second derivative is positive. F of x is concave down on -infinity to -2. Combine that interval with the 2 to infinity because f double prime of x is less than 0. Now normally, if the second derivative switches from a negative to a positive, we would say that this value is an inflection point, and same with this one. But because they're vertical asymptotes, we can't classify them. So in this case, there's no inflection points. So that's no changes in concavity. We're not going to get a smile and then all of a sudden a frown, or have a frown and all of a sudden get a smile. So there are no changes in concavity. So no inflections. Here is key information. So now I'm just going to use this information to check my graph. Is my graph smiling between -2 and 2? Yes, it's doing a smile. Is my graph doing a frown between the other two sections? So that's kind of in the middle of a frown. That's also in the middle of a frown because that curve is sort of opening down. So this represents the graph, and let's just summarize here. Y equals 2x squared minus 9 over x squared minus 4. Now the intent is to make sure you don't use your calculator on any of these sections. So any of the tasks I give you, you're expected to do this all by hand and show all of the steps like I did and be able to justify how you sketch the graph based on kind of the characteristics you're getting. So this is our first full example of curve sketching. So what I would like you to try before another time, and I'm going to have another video set up for this, is I would like you to try the function. Actually, I probably won't have a video set up, but I will have the solution to this one. Go ahead and try this example. It's not a rational, but it's moving a little bit into the radical functions. So go ahead and try that example after you've completed this lesson, and then kind of check your work through either the video or the solutions that will be posted.